Welcome back. In this video, I'm going to solve exercises 18 and 19 of chapter 1. Okay, exercise 18. We are given a metric space X, a point A in X, and a positive number R. So we have to prove 4 inclusions. The closure of the open ball of center A and radius R is contained in the corresponding closed ball. The open ball is contained in the interior of the closed ball. The boundary of the open ball is contained in the sphere of center A and radius R, which is by definition the set of all elements of the space whose distance to the center is exactly equal to the radius. So it's the closed ball without the open ball. And same thing, the boundary of the closed ball is also included in the sphere. And we have to give examples where equality fails. So we don't always have equalities. However, when we work in Rn with any norm, then all the above inclusions are in fact equalities. Okay. Now, first question, the closed ball is, we know that the closed ball is a closed set. We proved that. Okay. So, and it contains the corresponding open balls, but the closure of BAR is the smallest closed set containing BAR. Therefore, B prime AR contains BAR bar. Okay, so this is almost straightforward. And second thing is also similar. Now, of course, we have to give a counterexample. If we take any set having more than 1 point and we put on this set the discrete distance, which is just 0 if the 2 points coincide and 1 if not, then we know actually that the open ball of center A and radius 1 is reduced to its center. Okay. And so the closure of this open ball is the closure of the singleton A. But we know that in any metric space, singletons are closed. And therefore, the closure of A is A. So the closure of the open ball is just the center, whereas the corresponding closed ball of center A and radius 1 is the whole space. Okay, we proved that in the lectures. Okay, so note here one specificity of this discrete distance. Singletons are closed and open at the same time. Okay, this is not true in any metric space. This is really something really particular to this extreme case. So we don't have equality here because this term is A and this term is the whole space. So if the space is not reduced to a point, we don't have equality. Okay. Now, second inclusion, very similar because the open ball is an open set and it's contained in B prime AR, the corresponding closed ball, but the interior of this closed ball is the biggest open set contained in this set. So therefore, it contains BAR. So almost straightforward. And counterexample, same thing, take the discrete set. We know that, so the closed ball of center A and radius 1 is the whole space, therefore its interior is the interior of the space, which is the space itself, because any space is open in itself. Okay, whereas the open ball of center A and radius 1 is just the center. So here we have, we don't have equality if the space has more than 1 point. Okay, 3, the boundary of the ball is contained in the sphere. This is straightforward as well because according to 1, the closure of the open ball is contained in the corresponding closed ball. So when I remove BAR, I get this inclusion. But this term is just the boundary by definition because the open ball is open, so the closure of BAR minus BAR is just BAR, the boundary, the closure of BAR minus the interior of BAR. Okay, so this term here is actually just the boundary. So if you go back to the definition, you get the closure minus the interior, but since this is open, it's equal to its interior. So this is just the boundary. And this is by definition the sphere of radius A and of center A and radius R. So we have the boundary of the ball is contained in the sphere, and we have to give an example. So same thing, discrete space. The boundary of the ball of center A and radius 1 is the boundary of the singleton A. What is the boundary of the singleton A? It's the closure minus the interior, but the singletons are both open and closed. So this is just A minus A, and therefore it's empty. Now, once again, these relations are not true in any metric. So in any metric space, singletons are open, but not necessarily. Excuse me. In metric spaces, singletons are closed, but not necessarily open. Okay. And however, the sphere of center A under this one is just the closed ball minus, so it's just the whole space minus A. Right. So it's because every point different from A is at a distance 1 from A. So so we don't have equality here. Okay, so this is empty, this is x minus A. Okay, and same thing for the boundary of the closed ball. It's also contained in the sphere because the closed ball is a closed set. So the closure of B prime is just B prime, okay, because it's closed, and therefore the boundary of B prime is contained in the sphere. Okay, here we have this inclusion because BAR is contained in the interior. So the complement of the interior of B prime is contained in the complement of BAR. So pay attention to reversal of the inclusion. This is contained in this. Okay, therefore complementation reverse inclusions. Okay, and of course the same example works actually. The boundary of B prime, B prime here is the whole space, and the boundary of the whole space is the empty set, as we know. So because the whole space is open and closed. Okay, so any set which is open and closed has empty boundary. We said that in the course. Okay. And that's it. So now we move to Rn with any norm you like. Okay, it doesn't really, it's not important. Actually, all norms, we shall see that all norms are equivalent. Okay, so we have to prove now the reverse inclusion in part 1. Okay, so what we'll do now is to take an element here, prove that it's here, an element here, prove that it's here, and so on. Okay, so we have to prove the reverse inclusions. So take an arbitrary element x in the closed ball of center A and radius R. Now, what does this mean? It means that the distance, which is the norm of the difference, the distance between x and A is less or equal than the radius. So it's either strictly less or equal. If it's strictly less, then x is in the corresponding open ball, which is contained in the closure. So there's nothing to prove. The more interesting case is when the distance is exactly equal to r. What happens? So actually here x is on the sphere. Okay, consider this sequence. Xn equal x minus 1 over n x minus a. So this expression actually makes sense when we have the notion of sum of two vectors and multiple of a vector by a scalar. So we cannot define this in an arbitrary metric space. So this is why it didn't work. Okay, so what's the meaning of xn? So I suggest that you draw a picture here. So you draw the ball of center A, and you take x on the sphere. Okay, and now take a point xn, which is very close to x, but it's inside the ball. So we have, if you like, a, xn, and x on the same line, on the same ray, if you like. So you can easily check that xn is in the open ball of center A and radius r. Why? Because if you subtract a, you'll get here x minus a, x minus a. You'll get x minus a in common, and you get 1 minus 1 over n x minus a. And when you take norms, you'll get r times 1 minus 1 over n, which is r. So xn is inside the ball. And of course, since this term tends to 0, xn converges to x. And therefore, we know by proposition 1.8 that x belongs to the closure of the open ball. So we took an element here and we proved that it's here, and therefore we proved the reverse inclusion. Okay. Now, for the second inclusion, we take x in the interior of the closed ball, and you have to prove that it's in the open ball. So we reason by contradiction. If x does not belong to the corresponding open ball, then its distance, so actually if x is in B prime, is in the interior of B prime, then it is in B prime. So its distance to the center is less or equal than r. But it's not strictly less, because x, we are assuming that x is not in the open ball. Therefore, the distance is precisely exactly equal to r. Okay? And once again, now we consider this sequence, but this sequence now is outside the open ball. If you draw a picture, you get the center is here, x is on this sphere, and xn is slightly outside. Okay, so in question 1, we had xn was inside. So now, but the idea is the same. We are approximating x here in this case from outside the ball. Okay, whereas in the previous case, we were approximating x from inside. So please draw a picture. And now it's very easy to check that this sequence is outside. So it's in the complement of the closed ball, because the distance from xn to a is 1 plus n times r. So it's strictly bigger than r. Okay? So xn is in the complement of B prime and converges to x. Okay. So therefore, by proposition 1.8, the limit belongs to the closure of this set, which is by exercise 9 or something, I don't remember. The closure of the complement is the complement of the interior, right? This was proved in a previous exercise. Therefore, x does not belong to the interior of the closed ball, so we get a contradiction. Okay, so this proves the reverse inclusion. Now, for the reverse inclusion of the unit sphere, we take actually here we don't need to, we can take an element in SAR and prove that's in the boundary, but we don't need that, because the boundary of the ball is by definition the closure of the ball minus the interior of the ball. But according to question 1, the closure of BAR is just B prime, and the interior, since the open ball is an open set, it's equal to its own interior. So this guy is equal to this guy. And therefore, when I remove BAR from B prime, I get the sphere. So we have just equality. And similarly for B prime, we go back to the definition. Closure of B prime minus the interior of B prime. But B prime is closed, so it's equal to its closure. And we proved in 2 that the interior of the closed ball is the open ball, and therefore we get the sphere again. Okay, so this concludes exercise 18. Please draw pictures. Exercise 19, an exercise about the boundary of a union of 2 sets. So we have to prove that the boundary of the union of 2 sets is contained in the union of their boundaries. First thing. And second question, we have to show that equality may fail. And third thing, we have to prove that we have equality if, in some sense, A and B are separated, in the sense that not only they are disjoint, we have something stronger actually, that B does not meet A bar and A does not meet B bar. Okay, so okay, and I gave you a hint. Okay, you will see why this is useful. Okay, so we go back to the definition. The boundary by definition is the closure without the interior. And we proved in exercise 3 that the closure of the union is the union of the closures. Okay, so I didn't change this. Now we also proved in this exercise that a circle union B circle is contained in the interior of A union B, and we don't necessarily have equality. This is also exercise 3. Therefore, when I take the complements, I reverse the order. Okay, so this guy is contained in this guy. Therefore, the complement is contained in the complement. Okay, so just have inclusion here. Okay, and now this is just I can rewrite this as A bar without the union of the interiors, union B bar without the same thing. Okay, this is just set theory. Okay, because an element is here if it's either in A bar or in B bar, but at any rate it's not here. So it's either in A bar and not here, or in B bar and not here. So if you like, we can write this A bar union B bar intersected with the complement of this. So if you apply distributivity of intersection with respect to union, you get this. Okay. And now, which one is bigger, A circle or A circle union B circle? Of course, this is bigger. So when I remove A circle union B circle from A bar, I get something contained in A bar without A circle. Okay. So this is contained in this. So complementation reverses inclusion, and same thing for the other. And I get finally, by definition, the boundary of A union the boundary of B. Okay, now question B, for a counterexample, you just take, I'll give you the idea and you work the details. If you take A equals 0, 1, it doesn't really matter if you take 0, 1 closed or open in this case, because, yeah, if A equals 0, 1, then the boundary of A is just 0, 1. The boundary of B is 1, 2. The union is 0, 2, and therefore this is 0, 2, and this is 0, 1, 2. So we don't have equality. And if you want a more extreme case, take A equal the rational numbers and B equal the irrational numbers. Then, as you know, the boundary of Q is R, the boundary of B is R. So I get here R. However, the union is R, and the boundary of R is empty. So we get here the empty set, and here R. So this is really extreme. Now, in question C, we'll do it in 2 steps. So first, we'll establish this relation, and then we'll use this relation to prove equality. How do you prove that? We try to go back through the steps here in this. So we have here a sequence of inclusions: equality, inclusion, equality, inclusion, equality. And to prove the reverse inclusion, we go from here. So we have to prove that this is equal to this, and this is equal to this, and this is equal to this, and so on. So this is the strategy. But first, we have to prove this relation. And how do we prove this relation? Just to have to prove the reverse inclusion. So we know that this is contained in this. So we have to prove that this is contained in this. So we take an element in the interior of the union and prove that it's there. So the condition that B bar does not meet A means that if X is in A, then X is not in B bar. And by proposition 1.8, there exists an open neighborhood O of X that does not meet B. Okay? So now, if X is in the interior of the union, then we have 2 things. First of all, X is in the union. So it's either in A or in B. So the strategy is to prove the following. If X is in A, we will prove that actually something more. We will prove that actually X is in the interior of A. And by symmetry, of course, if X is in B, then actually is in, because everything is symmetric. Okay, so suppose that X is in A, and let O prime be this open set. Okay, so this is the biggest open set contained in A union B. Now, if you consider the set, the intersection of O and O prime, of course, it's an open set. And it does not meet B because O does not meet B, okay? Because this is smaller. So if the big one is empty, the small one is empty. And second thing, the intersection is contained in O prime, which is the interior, which is contained in A union B. So what do we have here? This open set, O intersected with O prime, is contained in the union, but does not meet B. So what can we conclude from this? We conclude from this that it's necessarily contained in A, okay? How do you prove that? Take an element in the intersection, Y. Then it's either in A or in B, but it cannot be in B, therefore it's necessarily in A. So we conclude that necessarily the intersection of O and O prime is contained in A, and therefore it's contained in the interior of A, because the interior is the biggest open set contained in A, and therefore X is in the interior. So we proved that. We took an element X here, and we proved that it's in. If it is in A, then it is in A circle, and by symmetry, if it's in B, then it is in B circle, or you can repeat the reasoning, same thing. Okay, so this proves the hint, and now I will use the hint to go through the steps. Okay, so now I go back to the definition. The boundary of A union the boundary of B is A bar without A circle union B bar without B circle. This is just by definition. And according to what I said, a circle without A bar without A circle is the same as A circle I bar without A circle without B circle, because B circle does not meet A bar. So when I remove it, it doesn't change anything. Okay, so this guy is equal to this guy. And similarly for the other one. And now this is just A bar. This term is just A bar without the union, and this is B bar without the union. So I can write this as A bar union B bar without the union of the interior. So same thing. And according to the hint, this is exactly equal to this. So I get the boundary of A union B because it's the closure without the interior. So that's it. So this concludes exercise 19 and the video as well. So thank you for your attention. In the next video, I will start section 1.3.